When packages and dependencies break on a Linux system, the failures can look confusing because the symptom often appears far away from the cause. You might try to start a service and discover it will not launch, but the real problem is a missing library that was removed during an update. You might run a familiar tool and suddenly see errors about symbols, versions, or files that cannot be found, even though you did not change that tool directly. These moments feel like the system is fragile, but in reality, you are seeing the consequences of how Linux software is composed. Most programs are built from many pieces that fit together through shared libraries, configuration files, and package metadata. When one piece changes, everything that depends on it can wobble. The first response skill is to stop treating each failure as a separate mystery and instead treat package breakage as a dependency graph problem, where you identify what component is missing or mismatched and then restore consistency. This topic matters for Linux Plus reasoning because it teaches you to diagnose the category quickly and avoid risky, random fixes. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A good starting point is to define what a package is in the context of Linux distributions. A package is a bundled unit of software that includes program files, metadata about what it provides, metadata about what it requires, and instructions for how it should be installed and maintained. The package manager uses that metadata to install, update, remove, and verify software in a consistent way. Beginners sometimes treat packages as if they are just folders copied onto the disk, but packages are more like contracts. They declare, I provide this program and these files, and I require these libraries and these supporting pieces to function. When the contract is satisfied, the program runs reliably. When the contract is broken, you see runtime failures, installation failures, or upgrade failures. Understanding packages as contracts changes your response mindset, because you stop trying to manually glue pieces together and instead focus on restoring the contract that the system expects. Dependencies are the mechanism that makes those contracts meaningful. A dependency is a requirement that says a package needs another package, a specific version of a library, or a capability that must exist for it to work. The system's software ecosystem is built on shared components because that reduces duplication and allows updates to fix many programs at once, especially security updates. The trade-off is that changes to shared components can impact many programs. A common beginner misunderstanding is assuming that updating one package only affects that package, when in reality updating a shared library may change behavior for dozens of programs. Another misunderstanding is thinking that dependencies are always bad complexity, when they are also the reason Linux can receive targeted security fixes efficiently. In operations, dependency management is the art of keeping these shared relationships consistent and predictable across time. Package and dependency breakage usually falls into a few recognizable categories, and recognizing the category is what helps you choose what to check first. One category is missing dependencies, where a required library or package is not present, perhaps due to removal or a partially completed upgrade. Another category is version mismatch, where the required component exists but the version is not compatible with what the program expects. A third category is repository inconsistency, where the system is pulling packages from sources that are not aligned, leading to incompatible mixes. A fourth category is database or metadata issues within the package manager itself, where the manager's view of what is installed does not match reality due to interruptions or corruption. These categories often produce different flavors of symptoms, and your first response goal is to look for signals that tell you which one you are dealing with. If the error mentions a missing file, you suspect missing dependencies. If it mentions versions or symbols, you suspect mismatch. If many unrelated installs fail, you suspect repository or metadata inconsistency. Classification reduces panic and prevents the common beginner mistake of trying random reinstallations until something works. One of the earliest checks you should do conceptually is to ask whether the problem is happening during installation or during runtime. Installation time failures happen when the package manager refuses to install or update because it cannot resolve dependencies, because a repository is unreachable, or because it detects conflicts. Runtime failures happen when the package manager thinks everything is installed correctly, but a program still cannot run because something it needs is missing or incompatible. This distinction matters because installation time failures are usually about package metadata and repository alignment, while runtime failures can be about libraries, paths, or configuration. Beginners often blur these and treat them the same, but they lead you to different initial questions. If installs are failing, you focus on the package manager's ability to find and resolve. If installs succeed but programs crash, you focus on what the program loads at runtime and what has changed. Both are dependency problems, but they are surfaced at different stages and therefore have different first checks. A particularly common runtime symptom is when a program complains that it cannot load a shared library, which is a file that contains reusable code used by many programs. Shared libraries exist, so programs do not all carry their own copies of common functions, which saves disk space and allows updates to repair vulnerabilities in one place. The downside is that if a shared library is removed, replaced incorrectly, or moved, programs that rely on it can fail to start. Beginners sometimes interpret this as the program being broken, but the program may be fine. It simply cannot find its required building blocks. This is why the phrase dependency breakage is so literal. The chain of required components has a missing link. Another nuance is that libraries can exist but still be incompatible if the program expects certain functions that the installed version does not provide. In those cases, the failure may mention symbols or version references, which is your clue that this is not a missing file, but a mismatch between what the program expects and what is installed. Repository and source alignment is another major root cause, especially when systems mix packages from different release versions or from multiple sources that were not designed to work together. Linux distributions maintain repositories that contain sets of packages built and tested together, and when you pull a subset of packages from a different repository with different assumptions, you can create conflicts. A beginner may think more repositories means more options and therefore better, but in operations more repositories can mean more risk of incompatible combinations. This is especially important when dealing with core libraries or system components, because those pieces are deeply connected to many other packages. A common pattern in breakage is that a system partially upgrades, pulling some components from a newer set while leaving others behind, resulting in a mismatch that causes runtime failures. The first response thinking is to consider whether the system's sources changed recently, whether a major upgrade was started and interrupted, or whether a new third-party repository was added. You are looking for the reason the system might be holding a mixed set of expectations. Another category that beginners often underestimate is package manager state problems, where the database of installed packages becomes inconsistent due to interruptions, such as a power loss or forced reboot during an update. Package managers maintain records of what files belong to which packages and what versions are installed, and they may also perform post-install steps that finalize configuration. If the process is interrupted, the system can end up in a half-configured state where some files are updated and others are not, or where metadata says something is installed, but it is not fully set up. This is why it is risky to interrupt updates casually, especially on systems where package updates include kernel components, libraries, and service restarts. The symptom might be that installs fail, removals fail, or upgrades refuse to proceed because the manager detects an incomplete transaction. The recovery mindset here is to restore the package manager to a consistent state before you try to install additional software, because building on an inconsistent foundation compounds the problem. This is similar to file system consistency thinking. You restore the integrity of the management layer so it can reliably enforce contracts again. It is also helpful to connect dependency breakage to service startup behavior, because many learners first encounter it when a service fails to start after a change. Services often rely on both binaries and configuration, and they may also rely on libraries and helper tools. A service might fail because its main binary cannot load a library, because a helper program is missing, or because a configuration references a module that is not installed. Beginners sometimes treat this as a configuration error only, but dependency issues can produce configuration-like symptoms. For example, a configuration might be correct, but point to a plugin that belongs to a package that was removed. In that case, the correct fix is restoring the missing package, not editing configuration. The triage habit is to consider whether the failure message points to missing components rather than incorrect settings. This is why good incident response begins with reading errors carefully, because the language often hints at whether the system is missing a file, missing a capability, or rejecting a version mismatch. Dependency breakage also has a security angle that matters for Linux Plus, because keeping packages updated is one of the main ways systems receive security fixes, yet updates can sometimes trigger breakage if environments are inconsistent. Beginners can be tempted to avoid updates after experiencing one failure, but that creates long-term risk. The mature approach is not to avoid updates, but to manage them responsibly by maintaining consistent repositories, planning major version changes, and ensuring updates complete cleanly. When breakage occurs, the goal is to restore the system's package consistency so updates can continue safely, not to freeze the system in a broken or outdated state. This is also where the idea of knowing what changed becomes crucial again. If breakage followed an update, you look at what packages were touched and whether any core libraries were replaced. If breakage followed a repository change, you consider whether you introduced incompatible sources. This change-based reasoning prevents you from treating dependency issues as mysterious and helps you build a repeatable troubleshooting approach. A useful mental practice for first response triage is to focus on restoring a known good baseline rather than improvising. In package terms, a known good baseline means the system's installed set matches a coherent repository set, dependencies are resolved, and core libraries are consistent. Instead of manually copying files from random places or forcing installs that bypass dependency resolution, you aim to let the package manager do its job because it is designed to enforce the contracts correctly. Beginners sometimes try to fix one program by downloading a standalone binary or by manually placing a library file, but that can deepen inconsistency because the package manager no longer has an accurate picture of what is installed. Manual fixes can also create hidden future problems, such as the package manager overwriting your manual file on the next update or leaving behind orphaned files that confuse later troubleshooting. The safest pattern is to treat the package manager as the authority for system software state and to use it to restore coherence. This is not about being rigid. It is about respecting the system's own mechanism for maintaining consistency. It also helps to remember that not all dependencies are equal in impact. Some dependencies are optional enhancements, while others are core requirements that prevent a program from starting at all. Some packages are leaf packages that few other things depend on, while others are foundational libraries that many services share. Breakage involving foundational components tends to have broader blast radius, and the symptoms appear in many different programs, which can feel overwhelming. The right response is to recognize the pattern of broad impact and suspect a shared dependency layer rather than believing many independent failures happened at once. This is the same kind of reasoning you used in earlier topics like disk constraints and boot failures. When many symptoms appear simultaneously, look for the shared dependency underneath them. Package ecosystems are dependency graphs, and shared nodes can create shared failures. Once you see that, you can stop chasing each symptom and focus on the central inconsistency that is affecting many components. As we conclude, the most important skill is not memorizing any particular package manager behavior, but developing a calm first response checklist in your head that guides you toward the right category. Package breakage often shows up as missing dependencies, version mismatches, repository inconsistency, or package manager state problems after interrupted transactions, and each category suggests different first checks. The first question is whether the issue appears during install or during runtime, because that tells you whether to focus on dependency resolution or runtime loading. The next question is scope. One program failing suggests a localized dependency, while many programs failing suggest a shared library or repository problem. The final question is what changed recently, because updates, repository adjustments, and interrupted upgrades are common triggers. When you use that reasoning, you restore software consistency instead of applying random fixes, and you reduce the chance of creating deeper instability. That disciplined approach is exactly what Linux Plus expects you to internalize, because it demonstrates you can reason about systems as interconnected components, not as isolated commands.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.